Okay. Good afternoon, everyone. Um, Welcome to 141 episode of Creative Online Weekend Talk. I am Supriya Naika, host for this session. Creative is not just a group, it's a community of like-minded individuals driven by curiosity and creativity. As a name suggests, to fuel our active engagement with the world around us with our tagline Knowledge Square. We firmly believe that information is multiplied when it is shared. Our vision at Creative is to foster constructive thinking across various domains. We are committed to explore non-textual, non-academic, non-syllabus concepts, enriching our understanding of world in unconventional ways. Every Saturday, we gather online on Zoom and broadcast live on our YouTube channel Creative GBD. We extend our heartfelt gratitude to all our resource persons who are generously shared their expertise and passion with us, enriching our collective learning experience. For today's episode titled Fun with the Sun, we are privileged to have Professor Prajwal Shastri ma'am with her profound knowledge and expertise undoubtedly illuminate us on her fascinating topic. So let's start our journey of discovery together as we explore the mystery of our nearest star with ma'am. Thank you for joining us and let's make this episode of Creative Online Weekend Talk a truly enriching experience. Before start, I call Niharika to introduce today's speaker. Over to Niharika. You are muted, Niharika. 1 minute. Okay, go ahead.
Good afternoon to everyone. I am Niharika. I, being the students of Creative, here to welcome our today's speaker, Prajwal Sastry ma'am. Prajwal Sastry ma'am is an astrophysicist for over 4 decades. She investigated the physics of giant black holes that are found in the centers of distant galaxies using telescope at multiple frequencies. She got her PhD from the Tata Institute of Fundamental Research. She has been a Fulbright Fellow at Stanford University. She is currently Emeritus Scientist at the Raman Research Institute and Adjunct Professor ICRAR. She is extremely passionate about the science outreach. She believes that the cultivation of scientific thinking is for everyone. She is also deeply concerned about the inequities in the sciences and attempts to bring an intersectional lenses to the endeavors to mitigate them. She is founder and past chair of the Gender and Physics Working Group of Indian Physics Association and past member of Working Group for Gender Equity of the Astronomical Society of India. She is Vice Chair of the Women in Physics Working Group of the International Union of Pure and Applied Physics and was Vice Chair of the Executive Committee for the International Year of Basic Sciences for Sustainable Development. In addition to her research publication and popular articles on astrophysics, her published work includes her published work includes writing on gender inequity as well as science and society. I thank our creative team for inviting her to this talk. Over to Supriya, ma'am.
Thank you, Niharika. Thank you very much. Over to ma'am. You can start. Ma'am, you are muted. It's visible, ma'am. Ma'am, click on Unmute, ma'am. It's showing. Okay, 1 minute, ma'am.
Oh, okay, now it's fine.
Yes, yes,
Can you
ma'am.
hear me?
Yes, ma'am.
Yeah. Okay. Thank you very, very much, Supriya, and thanks to all of you for coming here for this event. I really appreciate the work that Supriya does, and I think it's an extremely good effort, especially because I think it's not only targeted at students of science, but it seems to be something which includes everybody, which is really nice. So Supriya told me that the occasion for this was Zero Shadow Day, which happened 2 days ago. And so I presume that all of you have done some kind of activities on that day. So Zero Shadow Day is not really zero shadow, but it means that if you keep something vertical, like in this photograph, on a horizontal surface, then on Zero Shadow Day, at the moment when the sun is directly above our head, those vertical objects will not have a shadow. And you know why that is, I'm sure. I will not go into great details about why the vertical objects will not show a shadow on that day. But there are a lot of interesting tidbits that you can learn if you've not already done so. So, for example, it is only the regions between 23-degree latitude north and 23-degree latitude south which experience this phenomenon. And the reason, of course, for that is the fact that the Earth's axis of rotation is inclined at 23 degrees to the plane of the orbit, and so on and so forth. So there are a lot of very interesting tidbits. I also saw this thing on the internet, which is a architectural construction by an artist in Hawaii. So as you know, the United States, most of the United States is above 23 degrees latitude, but Honolulu is below. So they can experience Zero Shadow Day. And apparently this sort of very strange looking architecture, sort of sculpture on Zero Shadow Day gives rise to a circular shadow in that, on that central sort of platform that is shown in the picture. So I thought that was really cool, and they call it La Haina Noon. And on Zero Shadow Day, of course, this happens, which is a date that is different for different parts of the Earth, obviously, because the sun is not overhead exactly on the same day for everyone. It will depend on the latitude. So these are all some little tidbits that I particularly encourage the younger people in the audience to look at and explore, and also involve everyone, your parents, your chikamas and dodamas, and your neighbors and everyone else around you. But then Zero Shadow Day is not, why do we do experiments like Zero Shadow Day? I think our sort of innate goal, obviously there is the goal of inciting your curiosity and getting you to do exciting experiments and thinking about why things happen the way they happen. But underneath all that is the idea that scientific temper is something that we need to build awareness about in everybody. There is not enough of that, despite the fact that in India, Indian society has embraced a lot of technology, such as mobile phones, such as very sophisticated medical diagnosis equipment, or such as excitement when ISRO flies missions to the moon and all of that. So there is this embrace of technology, but there isn't a concomitant embrace of what is the science underneath all of that, and therefore what is the scientific method, and what does that mean for our daily lives. It means scientific temper, which is also part of the Constitution, the Indian Constitution, and essentially what it is encapsulated in this quotation: the refusal to accept anything without testing and trial, and the capacity to change previous conclusions in the face of new evidence. And so that is a critical thing, that you change previous conclusions. You have the capacity, sometimes the courage to change previous conclusions in the face of new evidence. So that is kind of at the core of it. This is a page out of a book that I will refer to later, called Ask Why. And it's in this version, this is also a poster that some of us used for our work in this area. And it's in Kannada, and it says scientific thinking, and it says, as much belief as there is evidence. Puravi iddashte nambu. So this is a quote by Narendra Davolkar in Marathi, actually, Jevda Purava Tevda Vishwas. And it sort of encapsulates this core idea that we are trying to build awareness about when we do such experiments. And I want to say that this is not a modern idea. This is something that has been part of our tradition very strongly. So, for example, in Karnataka, I'm familiar mostly with what happened in Karnataka, and there is a lot of poetry also, which questions certain blind beliefs. For example, this one, which is a vachana or poem by a thinker called Basavanna, which says Kallanagara Kandade Halane Nemberu, which means that when you see a snake's figure made of stone, you say pour milk, but when the real snake appears, you say kill it. So what is this contradiction? So these ideas are very old. They're part of our tradition. So it's not as if it's something new that Jawaharlal Nehru talked about, but he, in that quotation, sort of encapsulated the whole thing, also encapsulated all the modern day progress that has come as a result of applying this kind of thinking. This is just another example from the 12th century, which questions astrology, for example. Zero shadow day experiments are not the only possibility of doing fun things with the sun. Daytime astronomy has a very wide range. And I just wanted to show you some examples. So there is something you can do using a ball and a mirror of projecting the sun. I'll get into that in a bit. There is also some very interesting demonstrations of the pinhole camera effect that you can do with a small mirror. And some of these experiments have been designed by friends of mine who work for an organization called Navnirmiti. And a few years ago, we created videos with the children doing some of these experiments, and all those videos are on YouTube. So that is something you can refer to there. And I'm going to ask Supriya to send all of you some of the material from where you can do this book. So on the right here, you see another set of experiments that one can do during the day with the moon. So as you all know, the moon is visible during the day on some days. So there are a bunch of interesting experiments that you can do with that, recording where you see the moon, at what distance from the sun, in what size, and so on, which way is it facing, and all of these kind of things. And so that is described. I wrote an article on this for a magazine called I Wonder. So this is a snapshot from there. And so I will have Supriya send you that article as well, in order that you might dabble in this, and maybe you can devise your own experiments taking cues from this. So this is this book that I mentioned before called Ask Why. It is available in many languages, and including English and Kannada, and I've sent the it's WhatsAppable. So I've sent the English and Kannada versions to Supriya, and she will share it with you. So it has a bunch of very, very simple experiments which anyone can do. So you can gather your family members and your neighbors around and friends around you and do these things and have a chat around them as to why you see what you see. And of course, these are published with Creative Commons license, so you can do whatever you want with them, convert them, clip them, translate them, do whatever. I even took that book to Ethiopia once when I visited there for a conference, and I took it to a school there and they also loved it. So it's something that has a lot of appeal. So one of the experiments there is the idea of projecting the sun's image using the pinhole camera principle. So it's something that can be done very simply. So you have, as you can see in the photograph, you have a ball. So can you see what I'm showing?
Yes, ma'am.
Okay, so this is like a regular ball that children play with. So what I've done here, and this is described in the book as well, Navnirmiti designed this experiment. So I made a hole in the ball and filled it with sand, that is just to give it some weight. And then I shut that hole. And then I took a mirror and pasted it on the ball. So you can see that this is a small mirror which is available in any kind of shop. And so then what one does is, on a flat surface, you keep a ring like this. So this in particular is what remained of a sticky tape or sellotape reel. So what I very meticulously collect them when the sellotape finishes. So if you have a horizontal surface and keep the ring on it and then keep this ball, then the ball, because of the sand in it, it's heavy, so it's very stable, and you can rotate it in any direction. So you can rotate this mirror in any direction like this. So in technical language, we call it as, so this angle would be the altitude and this angle would be the azimuth. So you can change the azimuth and the altitude like you can do in telescopes. And what this girl is doing here is she's trying to get the image of the sun to project onto a wall or a screen that has been kept in front of her. So for example, here, if I'm not seeing the sun directly from where I'm sitting, but if I could, then I could adjust this so that the image of the sun gets focused on, for example, the screen. So this is very, very simple. I don't know if you've noticed, but this business of Surya Tilak has been in the newspapers a lot, and a lot of people seem to be talking about it. And I'm getting all these sort of WhatsApp forwards and whatnot about Surya Tilak. So you could also do this. You could, in fact, pick a statue. Say, you probably have a statue of Gandhi or Ambedkar, or maybe if you are in Karnataka, then of Hosur Narasimhaya, who was a big champion of scientific thinking and so on. Also Gandhi and Ambedkar, they were not scientists, but they championed scientific thinking as a way of life. So you could pick their statue and construct this ball projector and do a Surya Tilak on their forehead. So that would be really cool, because it's a very, very simple thing to construct, as I explained to you. So that is the ball mirror experiment. So once you get hang of it, once you construct it and get the hang of it, one of the things you could do, for example, is you have a screen, a sort of biggish screen indoors, and have a fixed point outdoors from where you project the sun's image. And if you do this consistently every day, then on the screen, you will be able to see how the sun moves. and how fast it moves. You can even, once you get the hang of it and you're able to do it very consistently, then you can even measure how fast it moves. What does that mean for the sun's image to move? How does it move? Of course, it will move during the day. But if you then start to project it at the same time each day, will it fall on the same position on your screen? And if not, then why does it change? And how does it change? And how fast does it change? So these are all a bunch of experiments that can be done very, very easily with this piece of equipment that costs virtually nothing. And it's very, very simple to make. So all of these experiments, as I said, not all, but at least 17 of them have been filmed with children doing these experiments, and they're on YouTube. So you can take guidance from there as well. You can access these films. They used to be on the Vigyan Prasar website, but now Vigyan Prasar has been shut down. So that website is dead. But they're on YouTube, and the playlist, they're on the channel. If you go to my YouTube channel, I have a playlist called Suraj Zameen Par. And using that, you can access all these videos. They're in English and in Hindi separately. So these are just some screenshots from those YouTube videos. And this is the same projector that I just showed you, a similar thing made with a ball like this. And here you can see that this child has also got a cardboard box. So those YouTube videos describe how you can create an image inside a dark chamber. So this dark chamber can either be inside a cardboard box, or it could be even inside a room if you can find an appropriate place from where to project the sun into the building. And the advantage of that is that your room will be quite dark compared to the outdoors. If you see the weather outside now, it's extremely hot and it's extremely bright also. But if you take the sun's image using this mirror into a building, then you can get a very high contrast between the image of the sun and the interior of the building. So fundamentally, you see, what is happening here is that now suppose the sun is coming from there and I use this mirror to project it onto my hand, right? So then what will happen is I will basically see the shape of the mirror. I will see a square shape on my hand. And if I were to make this circular shape, the mask, then I would see a circular shape on my hand. And if I put a triangular shape, I would see a triangular shape and all of that. So there is an experiment which shows this also. It's called the magic mirror. So you could look for that as well. However, if I start to increase the distance of my hand from the sun, from this mirror, sorry, not from the sun. From the sun, it's a fixed distance. If I start to increase it at a certain distance, it will enter the pinhole camera regime. So this will function like a pinhole camera, except in reflection. And so then, no matter what mask is put here, whether it's triangular or circular or some star shape or some odd shape, like a shape of a duck or some flower, whatever it is, you will get a circular image because the sun has a circular shape. So that is when you know that you're in the pinhole camera regime. So it's a very fun experiment to do. This is just another photograph of that same, a snapshot or screenshot of the same experiment. So now I want you to think about what it actually means. So one of the things that is fascinating about doing astrophysics is to relate vastly different scales and vastly different sizes. So, for example, we know that the nearest cosmic object to us is the moon. how far is the moon? It looks rather big in the sky, so we might think, oh, it's not all that far. But if you think in terms of the speed of light takes more than a second to reach the moon. So the light has a speed of 300,000 kilometers a second, and the moon is about 400,000 kilometers away. So it takes more than a second for light from the Earth to reach the moon. And this photograph that I'm showing you, it was the first photograph which has both the Earth and the moon in the same frame. So this was a photograph taken by one of the satellites that went deep into our outer space, deep meaning in relative terms deep. And they took this image, so you can see both the Earth and the moon, and you can see that it's mostly empty space. And that is another hallmark of the cosmos, that it is mostly empty space, right? So that is one of the things that is very fascinating to get our heads around. That on the one hand, when we see the sky, we see so many stars in there. In fact, I'll show you a picture. We know that the solar system, so here is a typical picture of the night sky, if you like. Of course, this is taken from Ladakh, which has beautiful night skies. In most of the other parts of the country, we have spoiled our night vision with light pollution. So we don't see anything like this, but we might just see Orion, the constellation Orion, we may see a couple of planets. All these stars that we see are stars within our own Milky Way, right? And the solar system is just one among billions that is there in our Milky Way. So I showed you how there's so much of empty space between the Earth and the moon. There is so much of empty space between each of the planets and between us and the sun. So in terms of the speed, light takes more than 8 minutes to reach us from the sun. So if something happens on the sun, we will never know that it happened until 8 minutes later. So that is the kind of those are the kind of distances that we have to grapple with when we think about the cosmos. And so each of these bright shining spots is a star like our sun. Some of them are planets, of course. A few of them here and there are planets, but the rest of them all are stars, which are suns, like our own sun. And so they may have planetary systems around them. In fact, it's very interesting that as early as in the 16th century, a priest called Giordano Bruno in Italy thought about this. He contemplated the cosmos and he thought about this, and he predicted that every star will have its own planets. And this was not based on any observation. This was before Galileo turned the telescope on the sky and looked at a whole bunch of things like the phases of Venus and the satellites of Jupiter and all that. Well, before that, purely from theoretical considerations, Giordano Bruno made this prediction. And today we know that it is true. We have more than 5,000 planets outside of our solar system, which have been discovered. So more than 4,000 stars which have such planetary systems. So this, of course, is the Milky Way. You can see it go horizon to horizon. This is a picture from Ladakh taken by my friend Dorje Angshuk. I've never seen the horizon to horizon Milky Way here, but I have seen it in Australia because I once went observing to the Siding Spring Observatory, and that has a landscape which is absolutely fabulous, and you can see the Milky Way go horizon to horizon. And of course, this has been contemplated by humanity, by people for centuries. But during all those years, it was one thing that was not suspected was that there is a giant black hole in the very center of our Milky Way. So just think about what this Milky Way looks like. On the one hand, you have all these stars that you can see everywhere. They are all part of the Milky Way. Even though the Milky Way looks like this sort of band across the sky, all these other stars are also part of the Milky Way. The Milky Way now we know by studying the individual stars and how they move and all that, we know that the Milky Way has a structure that is like a spiral. That is, all the stars are like a spiral. And there is some amount of rotation of these stars around the center of gravity of this whole collection of stars, which are bound gravitationally to each other. But because we are inside that system, we are not at the center of that spiral galaxy. We are about 26,000 light years away from the center. So therefore, it seems like a band in the sky when we look skywards. And that is because sometimes we are looking in the plane of this spiral galaxy. Sometimes we are looking perpendicular to the plane, but then we are still seeing stars within the Milky Way. So if you look at this picture, if you look away from that band, which goes like an arch, horizon to horizon, we are looking at directions that are away from this sort of flattish spiral structure. So we are seeing stars in the Milky Way, but we are not seeing them. They're sort of seem like they're scattered all around. But in the direction of the spiral, because there are so many more stars, we are seeing it like a band across the sky. Now you might ask, why are there dark patches in this Milky Way? Is it that there are no stars there? So when Galileo Galilei first turned his telescope skywards, he realized that these bright patches that we see are because of billions of stars. But you might ask, what are the dark patches then? Is it that there are no stars there? Now we know that that is not true. There are dark patches because in between the stars, there are dust and gas particles. So I said that there is empty space between the Earth and the Moon, and between the planets, and between stars and all of that. That is technically not a very accurate statement. So it is mostly empty space, but there are very sparse particles of dust and gas spread all around. Now, the Milky Way is so large, as I said, the center of the Milky Way is already 26,000 light years away from us, that in our line of sight then, the number of dust particles becomes huge. So even though it's it's almost vacuum and very, very sparse, and so the dust particles are very, very sparsely distributed, more sparse than anything that we experience every day, either around us or in a laboratory. But yet the scales are so large that those dust particles shield the light from the stars behind them, because each dust particle acts like a little mirror. So when the light is on them, they scatter this light in different directions. Instead, it gets scattered elsewhere. Those dust particles get heated up, of course. And then they start emitting light in the infrared because they're warm. But this picture is taken in visible light, so we don't see that. If this picture were to be taken in infrared light, then we would see dust particles emitting. So all these dark patches are where there is more dust particles compared to the regions which are looking bright. Now, somewhere here in this band is the center of our Milky Way. And if you look at the sky and the Milky Way, it has this, it gives you this very serene kind of feeling. It's really beautiful. I mean, I hope all of you have seen the Milky Way with your own eyes. If not, you should definitely try and go to some dark place like this and see it. It gives you this very serene feeling, but in practice, of course, each of these shining dots is a star, which is a boiling cauldron. And many of these stars, if they are massive enough, much more than our own sun, then when they exhaust their nuclear fuel, they will collapse due to their own gravity and become a black hole. So it is estimated that there are about 10 million such black holes scattered all over the Milky Way. But what is really fascinating is in the center of the Milky Way is a very, very big black hole. And the evidence for this was found in a very interesting way. And I'm going to show you this result because it's one of my favorite results. So what you're seeing here in the top left corner is again a picture of the Milky Way, but a different view. And on it, you can see the yellow sort of diagram, which is the Sagittarius constellation, the so-called Sagittarius teapot. And near the spout of that, I've drawn a circle marked by the arrow. That is where the center of our Milky Way is located. That is the direction. Now, a team of astrophysicists used a telescope in Hawaii called the Keck telescope, which is shown in the picture there. And this team was led by somebody called Andrea Ghez, who's shown here in this slide. And what they did is they took images of that very center of the galaxy using infrared cameras. And so the rectangle that you see here is a representation of that image. The multicolored splotches that you see are real stars as imaged in the infrared. And on the top right corner of this rectangle, you can see a date. So what Andrea Ghez and team did is they took infrared pictures of the center of the galaxy starting in 1995 and then kept repeating it at regular intervals, and it continues even to this day. So basically they're taking images of that central part. So they're imaging the stars, and by imaging them at different times, they can see the shift in the position of the stars, and therefore they can figure out how the stars move, which is what you're seeing in this result. And so the curves which are drawn here are just for guiding the eye. And you can see that the data goes from 1995 all the way up to the end of 2022. But the data, I mean, they're continuing to take pictures. And the white cross in the center is not real data. It is just there for a very good reason. So what you can see here is that the stars are moving, of course. They're not moving in straight lines though, and they're not moving randomly. They're moving in elliptical orbits. And not only that, all the elliptical orbits have the same focus, which is what is marked by that crosshair. So what does this tell us? It's very reminiscent of our own solar system, where the sun is the most massive object of our solar system. And so it drives all the planets in elliptical orbits around it. So obviously here, there is something that is driving all these stars now. These are not planets, these are there's another thing that you can tell from this diagram, because we know we can measure the speeds with which these stars are moving. We can determine the mass of that central dark object that is driving all these things into elliptical orbits. And also, if you look at that star which is labeled SO2, it is the closest, and it does this elliptical orbit around this dark object, namely the crosshair. You can see that it approaches very close. But after closest approach, it continues to go on its elliptical orbit. There is no deviation. So there is no evidence of any kind of collision or anything like that. Which means that this dark mass, which is driving all of these stars, has to be smaller than the closest approach of this closest star. So we have a measure of the mass and we have a limit on the size. Putting these two things together, the only conclusion we can come to is that the mass is 4 million times solar mass, and it has to be a black hole. So that is the surprise, that in the center of our Milky Way is this giant black hole that is present. And it turns out this is not unusual at all. This is the case for every galaxy where we've looked at. Virtually every galaxy, which is a collection of stars, which is bound by gravity, seems to have a giant black hole in its center. So I think I will stop there and take questions because my main goal here was to try and show you how you can start with very simple experiments with a little ball like this and a mirror, and project the sun on various things, including your favorite statue or your favorite wall or whatever object. And then you can measure the speed with which these things actually move. And that gives you a sense of the size and scale of the cosmos. So if you actually look at the speed, for example, with which we are whizzing as the Earth rotates, it's about 0.5 kilometer a second. And if we look at the speed with which the Earth is orbiting around the sun, it's about 30 kilometers. And then when we look at the speed with which the solar system is moving around in the galaxy, in the Milky Way, that's about 250 kilometers a second. So these are mind-boggling speeds, but that's what it is. And that's what the study of the cosmos tells us. And all of this is not only for astrophysicists who do research on these things, but it is something for everybody to grapple with and get excited about. So I'll stop there.
Thank you, ma'am. Okay, Venkat, go ahead.
Hello, am I audible?
Yes, Venkat.
Yes.
Okay, thank you for your presentation. It was a wonderful one. I think it showed how small experiments can lead to bigger ones. But I wanted to ask here that, for example, you showed how we predicted the existence of a black hole. How could we say try to image it? Because we have only done it twice, and this is one of those black holes. So how could we say image one of these black holes? As last time we did this, we used almost all the telescopes around the world, including some in India, to image these black holes and then combine it into one image.
So you can't actually image the black hole because there's no light that comes out of the black hole. Yes. However, if you have a black hole and you have some matter, it might be stars or gas or something, which comes close to the black hole, then the black hole will draw that towards it. And in the process, the matter will get accelerated to very, very high speeds and therefore get heated to very high temperatures. So generally, if you have a black hole and the matter comes near it, typically the matter won't be heading directly towards the black hole. It will be having some speed of its own. So it will get drawn to the black hole and therefore it will first spiral around it before actually plunging into the black hole. And so before it plunges in, it gets heated and therefore it glows. And it is that glow that we can see. We cannot see the black hole itself. Right. And so if you have, we call that accretion. So the black hole is accreting stuff, meaning it is bringing stuff towards it because of its gravity. And so that accreting stuff is what glows, and that we can image. And so it's not an easy thing to image because of the scale. We don't have the technology to get very, very sharp images, the sharpest images that are necessary in order to image this stuff directly and look at its shape and all that. However, it has been done with a lot of advanced technology for two black holes, one which is in our Milky Way and one which is in another galaxy.
Yes.
And so that is the silhouette of the black hole. It's not the black hole itself that is measured, that has been imaged. It is the silhouette of the black hole. It did not actually involve telescopes from India because these telescopes were operating at millimeter frequencies. Only then you can get such sharp images. We don't have those telescopes in India, but millimeter wave measurements were critical. And so they were able to achieve a sharpness that is equivalent to me sitting here in Bengaluru and reading a newspaper in Delhi. That is the kind of sharpness of the image. And that can only be obtained using an array of telescopes which is spread across the planet, operating at millimeter frequencies. And so, yes, we have imaged two silhouettes, two black hole silhouettes.
Yeah, but we can use this image to figure out an approximate size.
Sorry, approximate what?
We can use it to figure out its approximate size and mass.
Of course.
Yeah.
Because we are measuring the silhouette.
Yeah, so we can figure out a threshold of, say, how far it is before that matter is sucked into the black hole.
Yeah.
Yeah. Thank you, ma'am.
Okay, Venkat. Ma'am, I posted your PDF files in chat box. Okay.
Okay.
Okay. Any more questions? Any queries? Raise your hand. I can unmute. Any questions? Okay, I'm unmuting. You can unmute yourself and you can ask the questions. Shobha ma'am, any questions?
Hello. No questions, madam.
Okay. No questions. Ma'am, tell me about your present work details, ma'am. What you are, ma'am, you are muted actually. Okay.
So I'm interested to look at what happens around these giant black holes when it accretes matter. So I study such black holes at different frequencies. So when you study them in, for example, X-ray light, then you're able to see this glowing stuff, not with a sharpness. So we just see a splotch. We don't see the shape of the material, but we can tell what is the temperature, and we can use the amount of light to come to certain conclusions about the giant black hole. I also look at, in the optical range, I look at the atomic spectra that we see from that same glowing material. And then if we take images at radio frequencies, then we are able to see the fact that this accreting material, it is heated to such high temperatures, it becomes plasma. And that plasma generates magnetic fields. And so then some of the stuff, instead of plunging into the black hole, is launched into different in two opposite directions away from the black hole, and so away even sometimes from the galaxy itself. So we call those as plasma jets, and so I'm interested in studying those using radio images, and then I try to look for connections between how these jets are produced and what they do to the environment of the galaxy itself, that is the environment around.
Excuse me, madam.
Yeah.
How exactly Chandrasekhar limit relates with the black hole?
Chandrasekhar limit doesn't directly relate with black hole. So the Chandrasekhar limit is for stars which are roughly the mass of our sun. So what it says is that so the thing is that all stars glow because of the nuclear processes which happen inside them, and so that is how they are able to retain that spherical shape, because the stars have a lot of mass. So if left alone, that mass would collapse due to its own gravity. But because this nuclear fusion is happening and all this power is generated, that keeps the star in shape. But once the nuclear fuel is exhausted, then there is nothing to keep the star in that way, and due to self-gravity, it collapses. Now the question is, how far will it collapse?
Okay.
So the Chandrasekhar limit says that if it is of mass that is roughly 1 solar mass,
okay,
then the electron degeneracy is able to act against and balance the self-gravity. So it will collapse until the electron degeneracy pressure. So the electron degeneracy pressure is that results in the fact that you can't have two electrons occupy the same state. So there is a pressure that is generated, and so that is able to counter the self-gravity. But if a star is more massive than the Chandrasekhar limit, then that degeneracy pressure is not enough to counter the self-gravity, and so it will collapse even further. So it will collapse into a neutron star, and then so that is where it has a very, very different physical characteristic. And if the mass is even more, so that limit is not very accurate. It's not as precise as the Chandrasekhar limit, but it is roughly 3 to something like 3 solar masses or something like that. And so if a star is even heavier than that, then it will not be able to even survive as a neutron star, and its self-gravity will go further and it will collapse into a black
hole. Is it possible to discover directly black holes using this Voyager something, possible to discover directly black hole? Possible?
So black holes are very hard to discover. The only way is either when they are accreting matter, so we discover them through the glow of the accreting matter, or we discover them through the gravitational effect. So for example, the giant black hole in the center of the Milky Way is not glowing, but it was glowing very feebly. So it was first discovered using the gravitational effect on the nearby stars. Of course, eventually we measured the silhouette, and that is due to the matter that is glowing, which is around the black hole, but it is still very feeble. Another way to discover black holes which are just floating around in space is through the gravitational lensing that they cause. So if they happen to pass in front of another star, and if we happen to be looking in that direction, then that star, the light from that star will get modified due to gravitational lensing due to the black hole. And we can see that, but that can only happen by chance coincidence, and so it's not that easy to do.
Okay. Thank you, madam. Thank you.
Thank you, sir.
Okay, thank you. Thank you very
Um,
much.
One question in chat box, ma'am. I'll read it. Ma'am, how was dust particle formed in space?
Yes, that's a good question. So dust particle formation requires, first of all, it requires molecules to form, and secondly, it requires the right temperatures. So in parts of space where the temperatures are rather low, molecules can form, and molecules, when they collide, they can come together to form particles of dust. So it's a very, very slow process of molecules coming together and forming compounds which are effectively dust, like silicon, silicates, and those sort of things.
Ma'am,
madam. Hello.
Dinesh
Can
sir. Yes, sir.
yes, ma'am. Madam, ಈ ಮಾಲಿಕ್ಯೂಲ್ಸ್ ಆಕ್ಚುಲಿ ಎಲ್ಲಿಂದ ಬರ್ತವೆ ಸ್ಪೇಸ್ ಅಲ್ಲಿ?
ಕಂಡೆನ್ಸ್ ಆಗಿ ಬರ್ತವೆ. ಅದರಿಂದ ಟೆಂಪರೇಚರ್ಸ್ ತುಂಬಾ ಕೆಳಗಡೆ ಇರುವಾಗ ನಮ್ ಲ್ಯಾಬಾರ್ಟರಿಯಲ್ಲಿ ಹೇಗಾಗುತ್ತೋ ಅದೇ ತರ. ಈಗ ಟೆಂಪರೇಚರ್ ಜಾಸ್ತಿ ಇರುವಾಗ ಅಯಾನ್ಸ್ ಇರುತ್ತೆ, ಆಮೇಲೆ ಕಂಡೆನ್ಸೇಷನ್ ಆದ್ರೆ ಆಟಮ್ಸ್ ಆಗುತ್ತೆ, ಅದಾದ ನಂತರ ಮಾಲಿಕ್ಯೂಲ್ಸ್ ಆಗುತ್ತೆ.
ಇನ್ನೊಂದು ಪ್ರಶ್ನೆ ಮೇಡಮ್, ಲೈಕ್ ಫಿಸಿಕ್ಸ್ ಅಲ್ಲಿ ಮ್ಯಾಟರ್ ಮತ್ತೆ ಎನರ್ಜಿ ಡಿಸ್ಕಸ್ ಮಾಡ್ತಿರಲ್ವಾ? ಸ್ಪೇಸ್ ಇಟ್ ಸೆಲ್ಫ್ ಹ್ಯಾಸ್ ಎನ್ ಎನರ್ಜಿ. ಐ ಮೀನ್ ಎಂಟಿ ಸ್ಪೇಸ್ ಅಲ್ಲಿ ಎನರ್ಜಿ ಇರುತ್ತಾ ಕ್ವಾಂಟಮ್ ಮೆಕ್ಯಾನಿಕಲ್ ಕಾನ್ಸೆಪ್ಟ್ಸ್ ಅಲ್ಲಿ?
ವ್ಯಾಕ್ಯೂಮ್ ಎನರ್ಜಿ ಅಂತ ಏನೋ ಇರುತ್ತೆ, ಅದ್ರಲ್ಲಿ ನಾನು ಎಕ್ಸ್ಪರ್ಟ್ ಅಲ್ಲ, ಅದರಿಂದ ನಾನು ಅದ್ರ ವಿಷಯ ನೀವು ಬೇರೆಯವರು.
ಅಲ್ಲ, ಹಾಗೇನಾದ್ರೂ ಮಾಲಿಕ್ಯೂಲ್ ಫಾರ್ಮ್ ಆಯ್ತಾ, ಹಾಗೇನಾದ್ರೂ ಆಗುತ್ತಾ ಅಂತ ಡೌಟ್ ಆಯ್ತು.
Molecules are directly it's matter itself. So I mean, if you're asking in the very beginning, hegaitu andre, very beginning energy was converted into particles, and then that into they were in ionic state, then atoms formed, and then molecules formed. As the universe started to expand, the temperature universe expansion leads to lowering of the temperature. At one stage, the temperature is such that molecular gas can form.
ಅಂದ್ರೆ ಇದಕ್ಕಿದ್ದಂಗೆ there is no formation ಅಲ್ವಾ? ಅಂದ್ರೆ ಇದಕ್ಕಿದ್ದಂಗೆ ಮ್ಯಾಟರ್ ಫಾರ್ಮ್ ಆಗಕ್ಕೆ ಸಾಧ್ಯ ಆಗುತ್ತೆ.
ಮ್ಯಾಟರ್ ಬೇಕು. ಹೌದು.
ಓಕೆ. ಆಮೇಲೆ ಇನ್ನೊಂದು ಪ್ರಶ್ನೆ ಮೇಡಮ್, ಸ್ಪೇಸ್ ಅಲ್ಲಿ ಆಕ್ಚುಲಿ ನಮ್ಮ ಬರೀ ಕಣ್ಣಿಗೆ ಏನ್ ಕಾಣಿಸುತ್ತೋ ದೇರ್ ಆಲ್ ರಿಯಲ್ ಒನ್. ಸೊ ತುಂಬಾ ದೂರ ಇರ್ತವೆ ಅಂತೆಲ್ಲ ಹೇಳ್ತೀವಿ. ಆಕ್ಚುಲ್ ಆಗಿ ಇವಾಗ ಆಸ್ ಆಫ್ ನಾವು ಅದನ್ನ ತಗೊಂಡ್ರೆ ಅದು ಆಕ್ಚುಲಿ ದೋಸ್ ಪಾರ್ಟಿಕಲ್ಸ್ ಆರ್, ಐ ಮೀನ್ ಸ್ಟಾರ್ಸ್ ಆರ್ ದೇರ್ ಆರ್ ನಾಟ್ ಅಂತ ಹೇಗೆ ಕನ್ಫರ್ಮ್ ಆಗುತ್ತೆ? ಬಿಕಾಸ್ ದೇ ಆರ್ ಆಫ್ ವೆರಿ ಫಾರ್ ಅಂತ ಹೇಳ್ತೀವಲ್ವಾ, ಸಮ್ ಲೈಟ್ ಇಯರ್ಸ್ ಇದಾವೆ ಅಂತ. ಸೊ ನಾವೆಲ್ಲ ಅಪ್ರಾಕ್ಸಿಮೇಟ್ಲಿ 100 years ಬದುಕಿರೋಂತ ನಾವೆಲ್ಲ. ನಮ್ ಲೈಫ್ ಸ್ಪ್ಯಾನ್ ಇಸ್ 100 years. ಸೊ ಈಗ ಸ್ಟಾರ್ ಇದೆ ಅಂತ ರಿಯಲ್ ಆಗಿ ಹೇಳೋದಕ್ಕೆ ಆಗತ್ತಾ?
ಇಲ್ಲ, ನಮ್ಗೆ ಗೊತ್ತಿರೋದು ಅದು ಅಲ್ಲಿಂದ ಬೆಳಕು ಯಾವಾಗ ಹೊರಟಿತ್ತೋ ಅದ್ರ ವಿಷಯ ಅಷ್ಟೇ. ಸೊ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, ಚಂದ್ರನಲ್ಲಿ ಏನಾಯ್ತು ಅಂತ ಅದು 1 second ಹಿಂದೆ ಆಗಿದ್ದು ಮಾತ್ರ ನಮ್ಗೆ ಗೊತ್ತಾಗುತ್ತೆ. ಸೂರ್ಯನಲ್ಲಿ ಏನಾಯ್ತು ಅಂತ 8 ನಿಮಿಷ ಹಿಂದೆ ಆಗಿದ್ದು ಮಾತ್ರ ಗೊತ್ತಾಗುತ್ತೆ. ಅದೇ ರೀತಿ ನಮ್ಮ ಆಕಾಶಗಂಗೆಯ ಮಧ್ಯದಲ್ಲಿ ಏನಾಗುತ್ತೆ, ಅದು 26,000 ವರ್ಷಗಳ ಹಿಂದೆ ಏನಾಯ್ತು ಅದ್ರ ವಿಷಯ ಮಾತ್ರ ನಮ್ಗೆ ಗೊತ್ತಾಗುತ್ತೆ. ಅದೇ ರೀತಿ ಬಿಲಿಯಾಂತರ ಜ್ಯೋತಿರ್ವರ್ಷಗಳಷ್ಟು ದೂರ ಇರುವಂತಹ ಕಾರ್ಯಗಳು, ಅಲ್ಲಿಂದ ಬೆಳಕು ಬಿಲಿಯಾಂತರ ವರ್ಷಗಳ ಹಿಂದೆ ಹೊರಟಿತ್ತು. ಅದರಿಂದ ಅದಾದ ನಂತರ ಏನಾಯ್ತು ಅಂತ ನಮ್ಗೆ ಹೇಳಕ್ಕಾಗಲ್ಲ. ಚಾಟ್ ಅಲ್ಲಿ ಒಂದು ಪ್ರಶ್ನೆ ಇದೆ, ವಾಟ್ ಹ್ಯಾಪನ್ಸ್ ಟು ದ ಡೆಬ್ರಿ ಆಫ್ ರಾಕೆಟ್? ಇಟ್ ಮೋಸ್ಟ್ಲಿ ರಿಮೇನ್ಸ್ ದೇರ್. ನೀವು ಅಂಡ್ ಇಟ್ ಭೂಮಿನ ಸುತ್ತುತ್ತಾ ಇರುತ್ತೆ. ಇಟ್ ಇಸ್ ವೆರಿ ಇನ್ಸ್ಟ್ರಕ್ಟಿವ್ to look at this video that NASA has produced of all the space debris that is rotating around the Earth. It is quite shocking, actually, as to how much debris we have produced without paying attention to what happens to that debris. So some of it will enter the atmosphere and burn and land up on the ground. Some of it will land up on the ground. If it is big, then it will land up in that sort of rocky form, and so on. From a rocket itself, it will mostly burn. But pieces of satellites are there floating around the Earth.
Just brief me, what are the activities going near Gauribidnur laboratory? Just briefly. Observe it.
Okay, I'm not very familiar with it. You should ask somebody from Gauribidnur to
You are not
talk about
working over there, ma'am?
No, I'm not working there. No. But they have a bunch of radio telescopes. They're observing the sun with some. They're observing neutron stars with some. Yeah.
Some, I met one sun-related researcher, so thought of it. Okay.
Yeah, so you should ask them. Yeah.
Okay. One more question, ma'am. Chat box.
How can you predict the age of the universe and other stars? So we can, because the universe is expanding, we can measure the age of things by looking at their spectra. So what is interesting is if you measure, let's say, the spectrum of I don't know, oxygen or something in the laboratory, it is the same oxygen atoms that give the same kind of spectra regardless of where they are in the cosmos. So we can we know the frequency at which oxygen spectra are emitted very, very precisely. Now, if we see, if we can recognize atomic lines of oxygen in the spectrum of an object in the cosmos through a pattern. If you have a single line, you can't recognize, obviously. But if you have a pattern of lines, so oxygen has a typical pattern of atomic lines. Nitrogen has similar, so does hydrogen, the Balmer lines, etc. So if you can identify such a pattern and be sure that this is oxygen or this is hydrogen, then we can measure the frequencies. They will not be the frequencies that we measure on Earth because it is very likely that whatever is emitting the oxygen lines or the hydrogen lines is an object that is moving, whether it is a cloud of gas or the atmosphere of a planet or whatever. So therefore, the frequency will be shifted by the Doppler effect, either blue shift or red shift, depending on whether it's moving towards us or away from us. So we can measure the line of sight speed. Now, in addition to this speed, because the universe is expanding, space-time is stretching. So these atomic lines will get shifted because of that stretching of space-time. So we can measure, so when something is really far away, then the Doppler shift due to its motion becomes relatively small compared to this shift due to the cosmological redshift. And so then we can measure how far it is. And how far means that light has taken that much more time to come to us. So then we get a handle on how early in the universe it was formed. And so this is one way in which we get a handle on how how large the universe is, how early that particular star or galaxy was formed, and so on. But then, of course, there is the whole business about studying the universe as a whole. So that's a complicated subject. It's a story for another lecture. And you should ask one of the experts. I'm not an expert on cosmological studies, so you should get a cosmologist to give you a talk on that. But they look at the overall structure of emission, the way it happened at the beginning of the universe. And at the beginning of the universe, as you know, there was this sort of what is called the Big Bang, that is the beginning of the universe. And then there were these non-uniformities, there were these density fluctuations in the matter, which then led to the matter sort of becoming more and more non-uniform. So in the parts which are high density, other stuff gravitates towards them, and so creates these sort of points of higher density and therefore points of lower density. And that gets reflected in the total emission that we see from very, very early times. So by studying all of this, you can come to conclusions about how old the universe is, and that has to match with so many other factors as well, because elements are also being formed at the time and all of these different things. So that is a whole very, very interesting and very fascinating study in itself, which I can't describe in just 1 or 2 minutes, but that gives you a sense of how that kind of quantification can be done.
Madam, one ಪ್ರಶ್ನೆ related to the formation of universe. ಇನ್ನೊಂದು ಬಿಗ್ ಬ್ಯಾಂಗ್ ಆಗೋದಕ್ಕೆ ಸಾಧ್ಯ ಆಗತ್ತಾ, ಅಥವಾ ಇನ್ನೆಲ್ಲಾದ್ರೂ ಬಿಗ್ ಬ್ಯಾಂಗ್ಸ್ ಹಾಗೆ ಇರ್ತವ? ಬಿಕಾಸ್ ವಿ ಡೋಂಟ್ ನೋ ವಾಟ್ ಈಸ್ ದ ಎಂಡ್ ಆಫ್ ಯೂನಿವರ್ಸ್, ಅಥವಾ ಯೂನಿವರ್ಸ್ ಎಕ್ಸ್ಪ್ಯಾಂಡ್ ಆಗ್ತಾ ಇದೆ ಅನ್ನೋದಕ್ಕೆ ಎಕ್ಸಾಕ್ಟ್ ಪ್ರೂಫ್ ಏನು ಅಂತ ಒಂದು 2 ಪ್ರಶ್ನೆ ಕೇಳಿದೆ, ನೀವೇ ಹೇಳಿ.
ಸೊ ಯೂನಿವರ್ಸ್ ಎಕ್ಸ್ಪ್ಯಾಂಡ್ ಆಗೋದಕ್ಕೆ ಪ್ರೂಫ್ ಏನಂದ್ರೆ, ವಿ ಸಿ, ನಾನು ಆವಾಗ್ಲೇ ಹೇಳ್ದೆ, ಸ್ಪೇಸ್ ಟೈಮ್ ಸ್ಟ್ರೆಚಿಂಗ್ ಇಂದ ಏನು ರೆಡ್ ಶಿಫ್ಟ್ ಆಗುತ್ತೋ ಅದನ್ನ ನಾವು ಅಳತೆ ಮಾಡ್ಬೋದು. ಅಂಡ್ ಇಟ್ ಆಲ್ ಫಿಟ್ಸ್ with this idea that the universe is expanding. So that is a very well established thing, because many decades of study show consistency with that idea. Whether there are multiple universes and all that, that at the moment is in the realm of speculation.
ಇನ್ಫಿನಿಟಿ ಅನ್ನೋದು ರಿಲೇಟಿವ್ ಕಾನ್ಸೆಪ್ಟ್ ಹೇಗೆ ಮೇಡಮ್?
ಇಲ್ಲ, ಇನ್ಫಿನಿಟಿ ಇಸ್ ಇನ್ಫಿನಿಟಿ.
ಅಲ್ಲ, ಈಗ ಇನ್ಫಿನಿಟಿ, ಹಾ, ಎಸ್ ಮ್ಯಾಮ್.
Yeah, I saw this comment by Nachiketa Sharma. Thank you very much.
Thank you, madam. Namaste. Namaste, madam.
Namaste.
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 Ma'am, I think we can end here.
Yeah.
Any more questions? I think no more questions.
Okay.
Thank you, ma'am.
Shall we start?
Yes, ma'am. Thank you for your insight and knowledge sharing with us, and we are truly thank you for your time and dedication to enrich our knowledge. Thank you, ma'am.
Thank you. Thank you.
Thank you.
Thanks for the opportunity.
Thank you, ma'am.